The fundamental theorem of arithmetic states that every composite number can be expressed as a product of prime numbers, and this factorization is always unique, regardless of the order of the factors. Let us understand this with an example. Consider the number 32,760. We can express it as 2 multiplied by 2 multiplied by 2, multiplied by 3 multiplied by 3, multiplied by 5, multiplied by 7, and 13. Writing this using powers, 2 cubed, times 3 squared, times 5, times 7, times 13. This specific combination of prime factors is completely unique to 32760. No matter which method you use, you will always arrive at exactly the same primes. This uniqueness is the essence of the fundamental theorem of arithmetic. Example 1. Can 4 raised to the power n ever end with the digit 0? For a number to end in 0, it must be divisible by 10. Being divisible by 10 means the number must have both 2 and 5 as prime factors. Let us examine the prime factorization of 4 to the power n. 4 to the power n equals 2 raised to the power 2n. The only prime factor here is 2. There is no factor of 5 at all. Since the prime factorization does not contain 5, the number cannot be divisible by 5. Therefore, 4 raised to any power n can never end with the digit 0. Example 2. Find the HCF and LCM of 6 and 20. We begin by writing the prime factorizations of both numbers. 6 equals 2 to the power 1, multiplied by 3 to the power 1. 20 equals 2 to the power 2, multiplied by 5 to the power 1. For the highest common factor, we take the lowest power of each common prime. The only common prime factor is 2, so the HCF equals 2 to the power 1, which is 2. For the lowest common multiple, we take the highest power of every prime present. LCM equals 2 squared, multiplied by 3, multiplied by 5. That gives us 4 times 3 times 5, which equals 60. Example 3. Find the HCF and LCM of 96 and 404. First, the prime factorizations. 96 equals 2 to the power 5, multiplied by 3. 404 equals 2 squared, multiplied by 101. For the HCF, we look for common primes and take the smallest power. The common prime is 2, so HCF equals 2 squared, which is 4. For the LCM, we use the formula, LCM equals the product of both numbers, divided by their HCF. LCM equals 96 multiplied by 404, divided by 4. Calculating, 96 times 404 is 38,784, and dividing by 4 gives us 9696. For two numbers a and b, we know the useful property, HCF multiplied by LCM equals a multiplied by b. But does this property hold for three numbers p, q, and r? Let us test with p equal to 6, q equal to 72, and r equal to 120. The HCF of these three numbers is 6, and their LCM is 360. The product of all three, 6 times 72 times 120 equals 51,840. But HCF times LCM is only 6 times 360, which equals 2,160. Since 51,840 is not equal to 2,160, the simple property does not hold for three numbers. The correct formula for three numbers is more involved. LCM equals P times Q times R, multiplied by HCF of all three, and then divided by the product of all three pairwise HCFs. Example 5. Prove that the square root of 3 is irrational. We use the method of contradiction. Assume the opposite. Suppose root 3 is rational. Then we can write root 3 equals a over b, where a over b is in its simplest form, meaning a and b share no common factors. Squaring both sides, 3 equals a squared over b squared. Rearranging, 3b squared equals a squared. So a squared is a multiple of 3. By theorem 1.2, A itself must also be a multiple of 3. Let A equal 3k for some integer k, substituting back, 3b squared equals 9k squared, which gives b squared equals 3k squared. Now b squared is a multiple of 3, so b is also a multiple of 3. But a and b were assumed to have no common factors. Both being multiples of 3 is a contradiction. Therefore, the square root of 3 is irrational. Example 6. Prove that 5 minus the square root of 3 is an irrational number. We use the method of contradiction. Assume that 5 minus root 3 is rational. Then we can write 5 minus root 3 equals A over b, where a and b are coprime integers, they have no common factors. Rearranging, root 3 equals 5 minus A over b. The right-hand side is rational, because 5, a, and b are all integers. This would mean root 3 is rational. But we have already proved that the square root of 3 is irrational. This is a contradiction. Therefore, our assumption was wrong. 5 minus the square root of 3 is irrational. Example 7. Prove that 3 times the square root of 2 is an irrational number. Assume the contrary. Let 3 root 2 be rational, equal to A over b, where a and b are coprime integers. Dividing both sides by 3, root 2 equals A over 3b. Since a, b, and 3 are all integers, the fraction A over 3b is rational. This forces root 2 to be rational. But the square root of 2 is irrational. This is a direct contradiction. Therefore, 3 times the square root of 2 is irrational. Exercise 1.1, Question 1. Express the following as a product of prime factors. Part, either number 140. Using the division method, 140 divided by 2 gives 70, 70 divided by 2 gives 35, 35 divided by 5 gives 7, 7 is itself a prime number. So 140 equals 2 times 2 times 5 times 7, which in index form is 2 squared, times 5, times 7. Part, to the number 156, 156 divided by 2 gives 78, 78 divided by 2 gives 39, 39 divided by 3 gives 13, 13 is prime. So 156 equals 2 times 2 times 3 times 13, which in index form is 2 squared, times 3, times 13. The fundamental theorem guarantees these are the unique factorizations. Exercise 1.1, Question 4. Given that the HCF of 306 and 657 is 9, find their LCM. We use the important property, LCM of two numbers equals their product divided by their HCF. So LCM of 306 and 657 equals 306 multiplied by 657, divided by 9. Let us calculate. 306 multiplied by 657 equals 201,042. Dividing 201,042 by 9 gives us 22,338. Therefore, the LCM of 306 and 657 is 22,338. Exercise 1.1, Question 5. Can 6 raised to the power n end with the digit 0 for any natural number n? For a number to end in 0, it must be divisible by 10. Divisibility by 10 requires the number to have both 2 and 5 as prime factors. Now let us factorize 6 to the power n. 6 to the power n equals the quantity 2 times 3, raised to the power n. This equals 2 to the power n, multiplied by 3 to the power n. The prime factorization of 6 to the power n contains only the primes 2 and 3. There is no factor of 5 anywhere. Therefore, 6 to the power n can never be divisible by 5, and hence it can never end with the digit 0, for any natural number n.